Hello, my name is Collins Njagi. I'm a third year student in Dedan Kimathi University in Kenya, and I'm going to be taking you through Fluid Mechanics 3. And today we shall look at momentum equations. So momentum equations, we have two categories: linear momentum equations for steady flow and angular momentum equations for steady flow. So in this video, we are going to look at linear momentum equations for a steady flow. And to start, we are going to have a small sketch. This is my control volume. At this point is point 1, and at this point is my point 2. So our fluid is entering at point 1 and leaving through point 2. At point 1, area will be area 1, density rho 1, velocity v1. At point 2, area is going to be a2, density rho 2, and velocity v2. So we are going to consider a small element of fluid, and it is traveling through a short time interval, which is represented by differential of t. So to start, we are going to look at the volume that is entering at point 1. So the volume at point 1. So volume is given by cross-section area multiplied by height. That is, if you had a cylinder, the volume of this cylinder is the cross-section area of this circle multiplied by that height. So the height is the distance traveled by this fluid. So height is the distance traveled by the fluid. Height is equals to distance, and distance is given by speed times time. That is going to be V1 differential of t. That is my height. Cross-section area, since we are considering a small element of a fluid, the cross-section area is going to be negligible. Alright. So with that, the volume at point 1 is going to be given by V1 differential of t. Secondly, we look at the mass that is entering at point 1. So the mass that is entering at point 1, then recall that density is given by mass all over volume. Therefore, mass is given by volume times density, whereby volume is cross-section area multiplied by height multiplied by density. Cross-section area is A1 at point 1 multiplied by height h. We found h is V1 differential of t. V1 differential t multiplied by density at point 1. So if you rewrite this, you shall have density 1, area 1, V1 differential of t. So that means the mass at point 2 will be given by density 2, area 2, V2 differential of t, because it's the same liquid at point 1 and at point 2. Then thirdly, we look at the force exerted by this fluid on the solid body. So the force exerted by the fluid on the solid, force exerted by the fluid. Now, from Newton's second law, we know that force is equal to the rate of change in momentum. So that means force is given by mass multiplied by acceleration. Acceleration is change in velocity divided by change in time. So acceleration is given by dv all over dt. Therefore, force will be given by m dv over dt. And we can write this to be d over dt mv, whereby mv is momentum. mv is momentum, mass times velocity. Okay, so let me rub at this point. So with that, to get the force exerted, it is going to be given by the change in momentum. Change in momentum, which is given by d over dt m2 v2 minus m1 v1. So m2 v2 minus m1 v1, whereby m2 v2 is the same as the mass that is entering, the one that we found at point 1, multiplied by the velocity. So that is density 1, area 1, v1 differential t, multiplied by velocity, this is point 2, multiplied by v2, while m1 v1 is given by density 1, area 1, v1 differential t v1. Okay, so with that, to get the force is going to be given by m2 v2 minus m1 v1 all over dt. So that is density at point 2, a2 v2 differential t v2 minus density 1, a1 v1 differential t v1 all over differential t. This differential t comes from the d over dt. Now at this point, differential t, and a t, so that cancels out, and I'm left with rho 2 a2 v2 v2 minus rho 1 a1 v1 v1. Now we are looking at linear momentum equations for a steady flow. So when we talk about steady flow, what does this mean? When we talk about a steady flow, that means that the volume, the amount of fluid entering is the same as the amount of fluid that is leaving. So that means that our flow rate Q is equal and is given by A1 V1, which is equal to A2 V2. Also, the same fluid is at point 1 and at point 2. So that means the density rho is the same as density at point 1 and density at point 2. So with that, we substitute into our equation, and from that we shall have density, it's similar, so that is density, then Q, A1 V1 A2 V2. So at that point, that is my Q2, and at this point, that is my Q1. But because they are similar, so if I can rewrite it, I shall have density Q2 V2 minus density Q1 V1. But since Q2 and Q1 is similar, I can have density Q V2 minus rho Q V1. 1, and this can be written as rho Q is equal to V2 minus V1. So the force exerted by the fluid on the solid body is given by density multiplied by flow rate into brackets velocity at point 2